Can you hear me?
Yes.
Okay, thanks. Okay, so first of all, I would like to thank the organizers to give me this good opportunity to present our recent work. I'm Hui-Ke Jin, a postdoc from TU Munich, and today I slightly changed my title, so I'm talking about the matrix product state for Hartree-Fock-Bogoliubov wave functions and the application to density matrix renormalization group. This work is based on several papers and is done with several collaborators. Professor Yi Zhou, he's from Institute of Physics in Beijing, and Professor Honghao Tu is from TU Dresden in Germany, and Dr. Rongyang Sun, who recently moved to RIKE in Kobe. Okay, so I think in this audience, I don't have to say too much words about tensor network. So I would like to have a very brief introduction to the Hartree-Fock-Bogoliubov wave functions, which are widely used as variational ansatz in many fields like condensed matter physics, nuclear physics, and quantum chemistry. The most general case of the BCS Bogoliubov wave function, I guess, is the BCS wave function, with all spin-4 fermion paired up in a spin wave. This wave function has been used to describe the conventional superconductor. Also, people have used this wave function a lot to understand unconventional physical phenomena in strongly correlated systems, such as high TC. For example, based on the BCS wave function, people can restore the gauge fluctuation by applying the Kurzweiler projection to remove some local degrees of freedom. So here we use a spin half as a case. Then at each site, we have 4 local states before projection. So we have a vacuum state, the holon, and spin up, spin down states, and doubly occupied state, the doublon. And the Kurzweiler projection means we only keep these two single occupied state. Then essentially we can obtain spin half many body wave function from the BCS state. So actually after projection, the BCS wave function is a kind of RVB state, which is used by Philip Anderson for understanding high TC and quantum spin liquid. The idea is that the projected BCS state can mimic some strong correlations of electron and then can serve as a variational wave function for TJ or Hubbard model. And meanwhile, MPS is also widely used as variational approach to quantum many-body systems. So we can have very natural question. Can we use some? Can we make some genetic connection between Hartree-Fock-Bogoliubov wave functions and the matrix product state? At first glance, this question sounds boring because people can always use DMRG to compute a BCS-like ground state. However, you will find that in fermion system, for example, the Hubbard model, DMRG is more accurate for strong interactions. And when interaction is weak, the DMRG is less efficient due to the strong entanglement in real space basis. And actually, this question is more interesting than we thought. And besides our paper, so there are already many good references for this topic. And also, we can get a lot of benefits from this approach. First, the Bogoliubov Hartree-Fock wave function is physically motivated. For example, we can start with a microscopic Hamiltonian, many-body Hamiltonian, and we can do some mean field theory and also do DMRG optimization. If the mean field theory can be compressed as MPS, we can compute the overlap between mean field theory and many-body state to understand the numerical data to clarify the ground state and to establish some low energy effective theories. And we also can go beyond the mean field theory by imposing Kurzweiler projection to study the fluctuation upon the mean field theory. And for example, for high TC, it is just the gauge theory with, so people can consider the fluctuation around some saddle point solutions. And once we consider the Kurzweiler projection, you will find this approach is very cheap. The usual method to handle Kurzweiler wave function is variational Monte Carlo. So you have to calculate some determinant of Faffian to impose Gutzwiller projection. But here we have MPS representation. So we can just easily remove some local degrees of freedom of each local tensor. And then some physical observable like internal entropy can be easily computed. And the final point is that this physical motivated wave function can be possibly used to initialize the DMRG computations. For example, in this middle region, DMRG is very bad. So maybe with some physical intuitions, we can prepare some initial state to help DMRG in this region. Okay, so this talk is about how to convert Hartree-Fock-Bogoliubov wave function into MPS. And here we would like to provide two methods. In the MPO-MPS method, we will derive a tensor network representation for Bogoliubov wave function and compress this tensor network into MPS. And also later we'll introduce a Faffian method. For this method, we will use some property of a fermionic Gaussian state. So we will directly convert a reduced density matrix of a Gaussian state into a MPS tensor. And we will mainly use the Kitaev honeycomb model and the Kitaev chain as benchmark models to show our numerical results. Okay, so first I will go through the MPO-MPS method quickly. So here we will not start with the BCS wave function. Instead, we would like to start with the n-particle BDG system. So with pairing terms, and we can diagonalize such a system by using standard BDG transformation. So we can obtain this BDG with all eigenenergies are negative. And this means the BCS wave function is actually a fully occupied state of Rose D dagger operator, the Bogoliubov quasi-particles. And notice we have to create this state on top of a vacuum of D fermion. And since we have a particle hole transformation, so this vacuum, the 0D state, does not have to be the same vacuum of original C fermion. But here in this formalism, because it is fully occupied, so we therefore, as long as the original vacuum has a non-zero overlap with this new vacuum, we can create those Bogoliubov D-deck operators on top of the original vacuum to obtain the same state up to only up to a phase vector. Okay. So notice the original vacuum is a product state. So it is an MPS with bond dimension D equal to 1, which can be easily set up. And here we would like introduce the key idea of the MPO-MPS method. Namely, we rewrite the single Bogoliubov quasi-particle, the dagger operator, as a matrix product operator MPO. This is very straightforward. So because if you multiply this rank 2 matrix, you will find the summation over the C and the C dagger is just those rank 2 product of this rank 2 matrix. So here we have a MPO with one dimension D equal to 2. And if you don't want to work with the fermionic basis, you want to work on some bosonic basis like a spin basis, you can easily convert this MPO into a spin representation by using Jordan-Wegener transformation. And the MPO is still a bond dimension 2 MPO. Only you have to replace this identity operator by this polymatrix. And for easily illustration, so we like to use this graphic representation of MPO. And here is this is the entry of each MPO for each local site. And okay, so now we have a initial vacuum state as MPS, and we have occupied quasi-particle as MPO. We just act all of those occupied single particle one by one into the vacuum state. So namely, we will contract all of those physical bonds of MPO and MPS from D1 dagger to DN dagger. in the end, we obtained this tensor network representation of BCS type state. And this MPO-MPS representation is exact, but computational is very hard. So in practice, what we want to do is compress this tensor network into MPO. The approach is, for example, we act the first operator, the D1 dagger, into the vacuum. If we do this contraction, so we obtain an intermediate MPS with only one particle occupied. Okay, and we can do it again, so we can obtain MPS, intermediate MPS with two particles occupied, and we can do n steps, so it's just like a time of evolution MPO algorithm, and eventually we can convert a BCS type state into MPS. However, the MPS compression can be very expensive since we have n MPO and n is the same as the system size. Then the bond dimension will grow exponentially because once we apply MPO into MPS, the bond dimension of the original MPS will be doubled. It means we need to truncate MPS in each intermediate step. Since we have so many MPO evolutions, in order to achieve a high fidelity compression, we need to suppress the entanglement growth over the MPO involved MPS. However, usually the wave function of Bogoliubov quasi-particle, because the basis is a block basis, so they are spatially extensive. So when you naively use these D fermions, the MPO-MPS method will totally break down because the large accumulate truncation errors. So a crucial point of our MPO-MPS approach is that we should use so-called maximally localized one-year orbital, the F fermion, rather than the D fermion. The F fermion are a linear superposition of the D fermion, which form a complete basis in the Hilbert space spanned by D fermion. So here we can simply replace the product of D fermion by the product of F fermion and change nothing. And each F fermion is designed to be spatially localized. So it only locally changes each intermediate MPS and can introduce a very small truncation error. And we have the setup of the one-year orbital, and we can arrange them in a proper order. The order is so-called left mid right scheme. So for example, at first MPO, this MPO, the wave function is localized at the left boundary. So we act this into a vacuum state. And the next one, the second one is localized at the right boundary. So we act this, and those are locally changed MPS and so on. And it allowed us to have a very slow entanglement growth. Here we show some results from the 1D Kitaev chain. The y-axis is the half chain entanglement entropy. So naively you can think this quantity, if this quantity is larger, the truncation error will be larger because we need larger bond dimension to capture the state. Okay, so if we use the original D fermion to occupy the vacuum state from lowest energy to the highest energy, you can see the entanglement entropy grows quickly, and the entanglement entropy of some intermediate MPS is even larger than that of the final MPS. Also, it means D fermion is very expensive. And if we use one-year orbital with left mid right scheme, you can see the growth of the entanglement entropy is much slower, and the accumulated truncation error will be very small. Okay. Okay, so here I have some words about Kurzweiler projection. And once we have MPS representation, the Kurzweiler projection is very easy. So maybe we can use the case of spin half system. We assume those two guys are on the same physical local lattice side. And this one is spin up and this one is spin down. And if you want to impose Kurzweiler projection, namely you only want to keep the singly occupied local state, you can contract those local two guys with a local Kurzweiler projection for each local site. It means the computation is local and it's very cheap. You can obtain a project MPS in just 1 second. And here we show that there are some benefits by using this wave function to boost the DMRG. And here we use the Kitaev honeycomb model as an example. And this is a Hamiltonian on the honeycomb lattice. The Kitaev honeycomb model is a very good example because it can be exactly solved by using four-Majorana decomposition, which can map the spin Hamiltonian into a free Fermion model coupling to a static Z2 gauge field. So the ground state of the Kitaev honeycomb model, it can be easily solved, and it is just a Gutzwiller project BCS wave function, which can be converted into an MPS by our MPL-MPS method. And by the way, if we put the Kitaev model on a cylinder geometry, we have we have a good quantum number. We have we have a twofold topological degeneracy due to the Wilson loop, the quantum number, good quantum number. The Wilson loop is just a product of sigma y operators along the purple loop C. So it is a Z2 number to label the ground state in different topological sectors. So here we use this model to benchmark the performance of traditional DMRG and Gutzwiller boost DMRG. The red line is the result of traditional DMRG, which is initialized with a random MPS. We can see that traditional DMRG requires larger number of swaps and a larger bond dimension to converge. And for green and the blue lines, we prepare the Gutzwiller project BCS wave function to initialize the DMRG. The bond dimension of the Gutzwiller wave function is very small, about 200. So the initial error is quite large. While the Gutzwiller boost DMRG can still converge more quickly and can reach a lower energy with a smaller bond dimension. So Gutzwiller DMRG is highly efficient if a right ansatz has been chosen. And notice here we prepare two different ground states in two topological sectors, the +1 sector and -1 sector. And during the swaps, this good quantum number, the Wilson loop, can be exactly preserved. It means by using Gutzwiller boosted DMRG, we can target different topological degenerate ground state at the same time. And this is very useful for studying topologically ordered state with the quasi degeneracy. And one interesting thing is that the traditional DMRG, which we have initialized the traditional DMRG with different random state, but it always converges to a phi y -1 sector, which has a higher energy. So it is around local minima. So it means for 2D, maybe traditional DMRG will trapped in a local minima. But if the initial state is correctly chosen, you can avoid this local minima. Okay, so let's now consider a less trivial case, the Kitaev honeycomb model in a 111 magnetic field. With the H field, the magnetic field, this model can no longer can be exactly solved. But we know some intuitions from two limit. So when magnetic field H is small, the ground state is approximately Kitaev's non-abelian state with Chang numbers equal to 1. And when H is very large, the state is a trivial polarized state. But for middle H, the ground state is, we don't know what the ground state is, but there are some wave function proposal like gapless U1 spin liquid with a spin on Fermi surface in former studies. So here we prepare those four Gutzwiller wave functions, and we use two quantities to quantify the quality of those four Gutzwiller wave function. The first one is the wave function fidelity, F tilde. So we consider a wave function from a converged DMRG, and also a wave function proposal from those four guys. And because they are both MPS, we can converge, so we can compute the wave function fidelity overlap, the wave function overlap easily. And and the other quantity is the fidelity of the reduced density matrix in the middle column of the cylinder. And this fidelity can suppress some boundary effect. So we can see For small magnetic field, for small h, the Kitaev's non-abelian state is a good ansatz. For both quantities, they have very high value. Sorry. And for large h, those two guys, I mean, the fully polarized state or partially polarized state with a trivial or non-trivial term number, turns out they are both works very well. But for middle magnetic field, both two fidelities tell us that none of those four guys is a good ansatz. So basically, we can use this method to see whether a Gutzwiller projective wave function is good or not, and it can make a bridge between DMRG and the version of Monte Carlo. Okay, so while the efficiency of MPO-MPS method highly rely on the choice of basis, but it is not very easy to find a well-localized one orbital in 2D and higher dimension. So sometimes the MPO-MPS method does not work very well for preparing a BCS type wave function. So here we would like to introduce an alternative approach, namely a Farfan method, which actually is inspired by the paper from Gardner Chen's group. The idea is that the BCS type state is a Gaussian state whose reduced density matrix can be exactly computed by using a correlation matrix trick. Once you have a reduced density matrix, you can pretend the eigenvalue of reduced density matrix, namely the Schmidt vector of the subspace or corresponding subspace. For example, so we have a Schmidt vector B state for M side subspace, and we have A state is the Schmidt vector for M-1 side subspace, and this guy Mn is a local state. And by definition, the MPS tensor is nothing but the overlap between those two guys. Okay, so let me first introduce what is the correlation matrix. Again, we start with a diagonalized BDG Hamiltonian, which is obtained by BDG transformation. U and V are corresponding BDG wave function for particle and whole parts respectively. And it is a free fermion system, namely the BDG vacuum is a fermionic Gaussian state. For this kind of system, all of the information can be encoded in the two-point correlation function because we can use the Hui-Ke theorem to obtain arbitrary multi-point correlation functions. So basically, the correlation matrix is nothing but I mean, with the elements being all possible two-point correlation function, and it can be represented by U and V, and it can fully characterize a BCS system. And now we consider a subsystem A. So because we want to consider reduced density matrix, so we consider a subsystem A consisting of M particle with that is J equal to 1 to J equal to M. And the reduced density matrix corresponding to this subsystem A is fully characterized by the omega A. Actually, omega A is the submatrix of the original omega. So here omega A, so we restrict the lattice index belonging to this subsystem A. And omega A is a Hermitian. It can be diagonalized by introducing Bogoliubov quasi-particle, but only within this subsystem A. And notice omega A still has a BDG form. So each eigenvalues of omega A comes in a particle hole pair. So if we have lambda p, we have a 1 minus lambda p, and lambda p is a real number in the internal of 0 to 1. Then by using the dA fermion within subsystem A, we can rewrite the reduced density matrix rho A in this simple form. Okay, so this guy inside the product, this guy actually is a diagonal 2 by 2 matrix. Okay, and rho A is a tensor product of those two 2 by 2 matrix. And if for example, if all lambda p are 1, you can easily see that rho A only have one non-zero element. It means rho A is a pure state. But in general case, I mean, lambda p is a real number, less than 1 and larger than 0. Then rho A has multi non-zero element. So rho A is a mixed Gaussian state. with each basis, with each eigenvalue is being a BDG vacuum. Okay, so we have this form. Rho A is a tensor product of independent two-level system. So we can define the Schmidt vector of rho A, which are a Fock basis of D fermion. And we use a vector NA to label this state. And N is a vector from N1 to Nm. And N is a integer, either 1 or a 0 or 1 corresponding whether the corresponding dA dagger operator is occupied or not. And we have Schmidt vector for arbitrary subsystem. But if we want to use them to compute the overlap, we need to rewrite those Schmidt vectors in terms of original C fermions. And here, dA fermion are very simple. We know the BDG transformation within a subsystem. So it's very simple. But here we have a BDG vacuum, DAD, 0AD, which changes as C subsystem changes. So firstly, we need to represent this vacuum in terms of original C fermion. And other BDG vectors can be obtained by particle transformation. Namely, we can interchange the certain column of the BDG of the Bogoliubov matrix and to obtain other Schmidt vectors. So we focus on this vacuum, and this state can be annihilated by all dA vectors. So the wave function of those dA operator are UA and VA. Within the help of block of Messier decomposition, we can bring UA and VA into a block diagonalized form. So namely UA bar and VA bar up to a unitary transformation DA and CA. And using this unitary transformation, we can define two canonical bases, FA and BA. And notice FA and DA share the same vacuum, and also BA and CA share the same vacuum. CA is the original fermion. And actually, the vacuum of FA fermion is easy to see by checking the element of UA bar matrix. And the vacuum of FA is just this state. So first, we have the identity block, and BA fermion in this block should be fully occupied in original vacuum. So we have these guys corresponding to fully occupied mode. And also we have null block, and the BA fermion in this block is an empty mode. So they disappear in our formula. And finally, for each two BA fermion in this remaining block are paired up in a BCS form. So we have this guy. And eventually, this Bogoliubov vacuum can be represented only by original fermion. And for other Bogoliubov vacuum, you can do same thing, just change some column of this matrix and use the new obtained UA and VA to do Bloch-Messiaen, and you can see this formula. And here we just rewrite this state in a more compact form. And now we know how to compute the Schmidt vector for arbitrary subsystem. And these two guys are Schmidt vector for two subsystems, and this guy is the local state. So by definition, this is the MPS representation, and by definition, the MPS tensor is just the overlap between those two states. And actually, in our formalism, we can rewrite over those two states in a very simple form, and the state share the same vacuum, so the original vacuum. So the overlap can be easily computed by using Hui-Ke theorem, and the overlap is nothing but a function of this big matrix and these wave functions. And notice here we don't need any canonical form of the MPS, so we don't have to compute the MPS tensor step by step. However, the calculation can be done in parallel. It means that if you have enough CPU cores, you can compute the entire MPS at the same time. And okay, before showing some numeric data, I would like to comment on truncation. Here, the MPS bound dimension is the same as Schmidt vectors, namely the bound dimension of reduced dense matrix, which increase exponentially with the subsystem size. So we have to truncate the reduced density matrix. Here we have two truncation schemes. One is the Gaussian truncation. It means we will directly truncate some Gaussian mode. For example, if one of this lambda p is very close to 1, we will let corresponding D mode always be occupied. Otherwise, if lambda p is close to 0, we will let this D mode being always unoccupied. So once we can fix one mode, and once one mode is fixed, the rank of the reduced density matrix will be reduced by half. So sometimes this scheme is too much. On the other hand, we can use SVD truncation by directly removing some state, some eigenstate corresponding to the eigenvalue of rho A. So this is the eigenvalue, and this truncation is more accurate. So again, in order to benchmark the performance of Pfaffen method, we use the Kitaev chain as an example, and we prepare the ground state of Kitaev chain by using either Pfaffen method as well as also MPO-MPS method, and at the same bond dimension. And we use the energy deviation to quantify the performance of those two methods. And here, the blue line is for MPO-MPS method, and the red line is the Pfaffen method. For relative R large pairing strength, the delta. Once the delta large, the energy gap is large. And in this case, the entailment entropy is very small, and both Pfaffen and MPO-MPS method work very well. And as delta is smaller and smaller, you can see the gap of Kitaev chain is closing. The ground state is more like a Fermi C, although it still have pairings. And you'll see the MPO-MPS method will become less and less accurate. The energy deviation is very large. However, the Pfaffen method still is good. And also in the inset plot, we show the result with very small delta. In this case, for both methods, the energy deviation decreased in a power law of inverse bond dimension. But you will find that the Pfaffen method lead to a much more steep decrease curve, so it is more efficient. And here we show why MPO-MPS method fail when delta is very small. Here you see that the entailment entropy of some intermediate state is even larger than that of a final state. So it means the one-year orbital we used here is not very localized. Well, the Pfaffen method does not depend on the choice of basis, so it is more reliable. Okay, so I think I have used a lot of time, and I will do a very brief summary. So we devised two simple methods to converge Hartree-Fock-Bogoliubov wave function into MPS, and we show Pfaffen method is more efficient, and we use some Kitaev model and K-honeycomb model to benchmark our result to see some benefits from this method. And actually, there remains some interesting questions. For example, can we generalize the Pfaffen method for bosonic Gaussian state? If we can do this, we can do a very efficient boson sampling. And also, it's very interesting to generalize this discrete formula into a continuum formula. Okay, so I will end up here, and thank you for your attention.
Thank you. Now the talk is open for question. Is there any question? Yeah, Jamin, please.
Hello. Sorry,
can you hear me now?
Yeah. Now I can hear you.
Yeah, I have a question on your this topological state result.
Okay.
It's a convergence about this one. It seems to me that if you use random MPS, then in a panel, then even for infinite bond dimension, you converge to a different state. And does it mean that it's stuck in a different stage?
Sorry. So you mean this one?
No, in the section, it's a 1/d versus the energy.
Yes.
And if I take this extrapolation to infinite d, it seems that the red line and the blue line would converge to different energies.
They converge to different energies. Here we only show the energy deviation corresponding to exact energy. So we know the exact energy. So here we just measure the energy deviation from the corresponding their own exact energy. So they converge to different state.
Yes, my question was, so it seems to me that the random MPS would converge to some would be stuck in some local minimum. It would never go to the state that's the blue line, from the blue line, right? So I just wonder what is that state? Do you look at
actually if you measure so this state actually is very close to this state. I mean, phi 1 minus 1 state. If you measure for finite size system, if you measure the overlap, you see the overlap actually is the order of this energy deviation.
Okay.
Yeah.
I see.
Yeah, but for infinity system, I'm not sure.
I see. And then another question is that, is there any fundamental difficulty to do a bosonic system? Because it seems to me that it's also straightforward.
Yeah, but you mean this for Pfaffen method, right?
Yeah.
So for this method, so basically for bosonic system, first, if you want to use the same trick, you will find, I mean, you don't have this formula. So basically, you also for bosonic system, if all modes are fully occupied or are fully paired up, you still have this kind of wave function, but you don't have this because you don't have Pauli because you don't have Pauli principle. So basically, it means the Fock space of boson is infinity. So if you can have this similar system, and for Pfaffen method, it's very similar. So the Fock space of a Gaussian state, a bosonic Gaussian state, the Fock space of boson is not a Gaussian state. So you can't directly use the Pfaffen method. You always have to, turns out you always have to compute a permanent, but for large system, the permanent is undoable.
I see. And the final comment. So there was a paper from Stephen White and Fishman. They can kind of convert an arbitrary Gaussian state to an MPS. It might be interesting to compare with this method.
Actually,
okay, again, it's listed here.
This paper actually, actually, this paper actually is very similar to our Pfaffen method because they convert a Gaussian state, but without pairing into MPS. So they also use some property of reduced density matrix. Actually, the orbital is quite localized because they use subspace. So the orbital will exactly within the subspace, but they use some gate he applies some gate to the initial state, which is very expensive. But so also it cannot be easily parallelized. Okay.
I see. I see. So your method would be physically the similar things, but it will be more efficient.
Yeah. The implement, our implement will be more efficient, but the system is very it's different. It's very same. Yeah.
I see. Thank you.
But here we also consider the pairing here, but they didn't consider the pairing, so the formulas are also a little different.
Okay. Thank you.
Okay. Thank you for question.
Okay. Is there any other question? Okay. I have one. So when you create a Bogoliubov vacuum, you have assumed that the system is open boundary. Is it possible to create the same, perform the same sort of operation for a periodic system under the periodic boundary condition?
Actually, you mean the real system is periodic or not, right? So basically, the result we show here is a periodic boundary.
I see. So in the real space, it's periodic. Okay. I understand. Okay. So please, Okunishi-san, go ahead. Okunissan?
Yes, okay. Thank you very much. So interesting talks. So I'm curious about the role of the transformation with some local Wanyi basis.
Sorry,
So,
which part? Sorry.
I think you used local Wanyi basis transformation.
Oh, so okay,
to-
okay,
to
sorry.
success.
The local. Let me move to this slide. Okay.
Yes, that's right. My question is, how can you determine this coefficient, transformation coefficient WLM within the framework of the tensor network? Because I think the role of this transformation is very similar to the disentangler using, for example, Mera, because this transformation suppresses the entanglement between the sites away from each other. So in this sense, I'm curious about this transformation.
Okay, thanks for a question. Actually, this is only, this trick can only be used in fermionic system because we have to use some Pauli principle. And actually, so the thing we did is that we first we use the wave function of D, and it is the polygon, and we project this D operator into the position into the position lattice. So something like local operator C dag L CL and CL C dag, and so you have a permission, you have an expectation value of the position operator as a matrix, and it is a symmetric matrix, and you can diagonalize this position operator, and you have some basis for this matrix, and so so this basis is just this one, the WLM. Okay, so you just project this wave function into the position operator, and you diagonalize the position operator. You can, the basis is the W operator is just the basis, the rotated basis.
You diagonalize.
Yeah, the position operator, but this operator can, but sometimes it can't work very well.
Oh, I see. For the case of Mera, we usually consider the two-site unitaries and optimize such a unitary with a very complicated Mera network. Yes, but in this case, just a diagonalization on the position representation gives this coefficient. It's a very interesting.
Okay, because it's free fermion system, we know all.
Basically free fermion system. Yes.
Okay.
But interesting. Thank you.
Okay. Thank you.
Okay. So time is up. So thanks to the speaker again. Thank you.